We're now going to begin looking at the various components of the molecular partition function, and we're going to start with the rotational components. Now, we learned back a few lessons ago that the rotational energy levels for a molecule, particularly a linear molecule, were given by a rotational constant times j plus 1. And I want to emphasize this is for linear molecules. All right, the rotational constant in this case is related to 1 over the moment of inertia for the molecule, and it's typically given in units of inverse centimeters or wave numbers. And as I mentioned before, this is due to the spectroscopic origins of this, and that we can convert these wave numbers to joules if we want to multiply by Planck's constant times the speed of light times this rotational constant. This would end up giving us energy in joules. All right, but back to this expression for the rotational energy levels. We also learned that these had a degeneracy. This is an intrinsic degeneracy, not an accidental one, an intrinsic degeneracy of 2j plus 1 for each of these levels. Because this is an artifact of the quantum mechanics for this system, I'm going to include that, but there's also another good reason to include it, in that it will make our evaluation of the partition function a little bit easier. So now if I write down an expression for the partition function, it'll look something like this. Z rot will be the sum over all the j values, so 0 to infinity, of this degeneracy, 2j plus 1, e to the minus beta times the rotational constant times j plus 1. All right, now this ordinarily would be a pretty difficult thing to evaluate, this kind of summation, but just as we did in the case of translations, it turns out that we can take this summation and convert it into an integration, because the rotational energy levels for most molecules are so close together that it makes that an equivalent sort of determination. I should mention that for those for which it's not correct, that is, that you can't make this substitution, I'm thinking of really light molecules like H2. It turns out there are few enough states that contribute to the partition function that one can simply evaluate those by directly adding up the states to get the partition function. But for others, where the rotational constant, where b is very small, this substitution of an integration for the summation is actually quite a good approximation. Now when we do that, that means that our rotational partition function could be written a little bit like this. 2j plus 1 e to the minus beta times the rotational constant b times j plus 1. And now we're going to treat that j as though it's a continuous variable. So we would be actually integrating over that j. Well, it turns out that this fragment down here is actually the derivative of this stuff up here. So it makes it actually quite straightforward to evaluate this integral. And we find that when we do that, we can directly write down that this integral is equal to minus 1 over the beta times the rotational constant, this is a beta, times e to the minus beta rotational constant, j times j plus 1, evaluated now from 0 to infinity. And of course at infinity I've got e to the minus infinity, which is 0. At j equals 0, I've got e to the 0, which is 1. So this turns out to simply be 1 over beta times the rotational constant. Or if I substitute in what beta stands for, I can put kBt over the rotational constant here. And this would be my final result. It's actually a really simple compact result. Now one thing I need to add to this compact result is that this would be true if my linear molecule did not have an element of symmetry to it. You know, something like HCl would be an example of a molecule that does not have an element of symmetry. H2, on the other hand, does, because when I rotate half the way around, I end up with a molecule that is indistinguishable from the original molecule. This is a formality or a very, I guess, picky point, but it means that when we define our rotational constant, we need to take this symmetry into account. And the way we do that is by injecting, if you will, another parameter in here, which is sigma, and sigma is basically a symmetry number. Now for linear molecules, the symmetry number is pretty easy. If the molecule is symmetric, then the symmetry number is 2. So this is if there is symmetry. If it's not symmetric, then it's just equal to 1. All right, but with this in here, we can now write down a rotational partition function that looks something like this. Now I want to introduce another little wrinkle in this that will give us a handle on how to classify different kinds of molecules. I'm going to define something called a rotational temperature. And this rotational temperature is going to come out of this expression for z-rot. And what it basically amounts to is that I've got a temperature in the numerator of this expression. So this other stuff out here, and I don't really have to include the symmetry number, but I have, but this other stuff out here must have units of 1 over the symmetry number because we know the partition function has no units. So in other words, I could define a quantity that looks like this, the rotational quantum number divided by Boltzmann constant. This is my rotational temperature. And I'm going to give this a special symbol. I'm going to say this is equal to capital theta with a little rot, and it's equal to this rotational constant divided by the Boltzmann constant. All right. So with this definition of the rotational constant, this will give us a handle on how to evaluate, if you will, the availability of states in different molecules. Now another thing I want to do is indicate that this Kb, we've listed it in various units, including joules per mole Kelvin and things like that. In this case, I'm going to use a unit for Kb that will help me get rid of the inverse centimeters that are in the rotational constant. And when I use units of Kb that are in inverse centimeters per degree Kelvin, the value for Kb is 0.6950346. So this is in inverse centimeters per Kelvin. So this is a number that you may want to make a note of and use as you do different problems involving this. Now let me show you what some of the typical values for linear molecules are. So what I've listed here are a set of rotational constants in this inverse centimeter unit, and I've then shown you their corresponding rotational temperatures, so you can get a handle for that. All right, as you can see, obviously these all scale. The bigger the rotational constant, the bigger the rotational temperature. But these are going, because the partition function tells us something about the availability of rotational states, and the rotational partition function is equal to T over the rotational temperature with the symmetry factor thrown in. But that means that this rotational temperature, the bigger it is, the fewer states are available rotationally. So for something like H2, which has a really large rotational temperature, this one has fewer states available. So large rotational temperature means fewer states available. It also means that high rotational energy levels are generally not populated very well. If I have a small rotational temperature, on the other hand, this means that many of the rotational states are available or are populated at a reasonable temperature. So you can see how this goes. The lighter the molecule, the higher the rotational constant and the higher the rotational temperature. As we move down this column, we're going from H2 to HCl to N2 to iodine. And so iodine is much heavier than these others, and you can see it has a really small rotational constant and a really small rotational temperature, which means that we would expect this molecule to have a lot of very high rotational states populated in general. Now, how would we determine the population of these states? Well, we would just generalize from our description of the probability. So the probability of being in the jth state is simply going to be the number of molecules in that state divided by that, or it's going to be this expression, e to the minus beta b j times j plus 1 divided by z root. But we have a very nice compact expression for z root up here, so it's essentially going to be something like 2j plus 1 e to the minus beta b j times j plus 1. And now we're dividing by z root, so that means that temperature will be in the denominator, and we'll have sigma times the rotational temperature up here. So this is a formula that you could use to determine, if you want, at a given temperature, what the probability of being in the jth state would be.